Today we'll be looking at the problem minimum area rectangle. This problem can seem kind of tricky at first, but once you really understand it, it's actually very simple. So the prompt is really short. We're given an array of points in the xy plane, where points I equals xi, yi, and we want to find the minimum area of a rectangle formed from these points. The sides have to be parallel to the x-axis and the y-axis. So that means we can't have a side going this way diagonally. The sides have to be parallel to our axes. If there is no such rectangle, we just return 0. So here we're given a list of points, and our output is 4. And you can see that the rectangle is formed by 4 points. We have 1, 1, 1, 3, 3, 1, and 3, 3. And the area of that is 4, since one side is 2 and the other side is 2, and 2 by 2 is 4. So let's dive a bit deeper into the example given. So there are actually 2 ways we could potentially do this. The first way I'll discuss briefly is actually an O of n to the 4 solution. And basically what we can do is kind of map all these points with their x value to the y value. And what that would look like is something like this. So say we take the x value of 1, and we want to map all of the y values that appear at 1. So we take 1 here, and have a list of 1 and 3. We'll do the same for 2. So we'd have 2 with a corresponding y value of 2, and then 3 with a corresponding y value of 1 and 3. So in laying it out like this, one thing that you'll notice is that 1 and 3 share 2 common y values. And you can see that here, that these 2 points lie on the same value of y. So what we can actually do is just check every single combination of points here, right? So we would do a nested loop O of n squared to go through our x-axis value. And then for each one of these, we would do another O of n squared loop where we go through all of the y values for each x-axis, right? So what that would look like basically is we would start at 1, and then for each one, go through every other value of x-axis basically. So we take 1, we just compare to 2, see if any 2 values in here share values to another, and you'll see that 1 and 3 do have 2 values in common. So we know that we can make a rectangle given 1 and 3 as x values, and then take points that are shared in common between those 2 values, so 1 and 3 here. And you can see that's the same rectangle we have in our example. So we have 1, 1, 1, 3, 3, 1, and 3, 3. Here you have 1, 1, 1, 3, 3, 1, 1, 3. So that's one way to do it, but there is one way that's a little less intuitive at first, but can actually speed this up by quite a bit. So there's a slightly simpler and more efficient way that we can do this. So let's take 2 points from our sample. Let's say we have 1, 1, and 3, 3. And let's notice that we specifically picked points that create a diagonal line. And why do we do this? So you can think about, what if we were to extend these lines out, or extend lines out from these points? So obviously from these points, these lines extend out infinitely in each direction, and I'll just kind of draw that out for you to see. And then similar for 1, 1, right? We know there are lines that are going to come out from each direction infinitely. So why did I draw these out? So if you remember from the problem statement, it said that any rectangle, the sides are going to be parallel to our axes, right? So what this means is that if we have these points, we know that any potential rectangle that uses this point has to include points along this line, right? So for 1, 1, this is going to be part of a rectangle. We can't have a point like over here or off here, right? We know that there has to be points on this line. Similar for 3, 3, right? We can't have a point down here or over here. We know that the point has to lie somewhere on this line or on this line if 3, 3 is going to be part of a rectangle. So you can kind of see here visually that there's a clear overlapping point that seems kind of obvious, right? Right here and right here. And looking at the diagram, it's like seems obvious you can make a rectangle from this, but from the code, how do we actually, figure this out and see what these points are? So if you examine the point that we're given in this diagonal, we have 1, 1. We can call this x1, y1. We also have 3, 3. And let's call this x2, y2. So you can see here that if we look at the intersection of these 2 points, so you look at this point here, the coordinates of this are 3, 1. You can kind of tell this just by looking at this graph. We go over on the x-axis 3, up on the y1. Similar here, if we look at this, this point is 1, 3. We're going over on the x-axis 1 and up 3. So as you can see, these points appear to have similar values to this diagonal we picked out. So what it actually boils down to is if we have a diagonal like this, we can pretty quickly check and see if it can make a rectangle with other points. Because we can check if this point is in our collection and also if this point is in our collection. So what we're actually doing is checking if x1, y2 is in our collection and x2, y1 in our collection. So if both of these are true, then we know that we can make a rectangle using these 2 points as a diagonal. And once we figure this out, very easy calculation to actually get the area, just do absolute value of x2 minus x1 times the absolute value of y2 minus y1, and that will give you your formula. So essentially what we're going to do is just compare every pair of points that forms a diagonal. So why don't we want to use points on the same line, right? Well, it just kind of makes our calculation more complicated, right? We see that if we use a diagonal, we're going to end up looking for those points on the line anyway. Just to keep our logic simple, we're just going to only look at these diagonals and then kind of extrapolate out from there to find those points on the other vertices. So basically what we're going to do is we're going to iterate through points. So for point, and then for each point, we're going to go through every other point. We're going to see if these points form a diagonal, and if they do, check for these counterpoints in the collection, and then calculate area. And we're doing 2 nested loops through points, so this is going to be O of n squared, which is a perfectly acceptable solution for this problem, and definitely better than our previous O of n to the 4 solution. So let's hop over to the code, and I'll show you exactly how this works. So the first thing we're going to do is create this set, which is going to hold our points. Then iterate through our points and just add each point to the set. We're going to create this variable called min area, which is going to hold the minimum area we've seen so far, and eventually will be returned as our answer. So then we're going to iterate through points, and then for each point, iterate through all the other points. Then to avoid diagonals, what we're going to do is say, if the x values of these pairs are the same, or the y value of these points are the same, we're just going to continue. We know that these are on the same line, they do not form a diagonal, and we do not want to check. Otherwise, we're going to do exactly what we lined out before. We're going to check if x1, y2 is in the points, and if x2, y1 is in the points. If they are, we're just going to calculate that area, and if it is less than the minimum area that we have seen, we're just going to update our variable. Then at the end, if we haven't found any rectangles, we're going to return 0, and we can tell that if our min area is still equal to infinity, otherwise return our min area. So let's submit and see if that works. And it does. So hopefully that was helpful. Thank you for watching. I hope you enjoyed it.